Buonasera a tutti. J'ai le plaisir et l'honneur de vous souhaiter la bienvenue à l'Université de Genève, au nom du département de formation continue et plus précisément du programme l'Italie, langue, culture et société. Mon nom est Federica Rossi, je suis didacticienne de l'italien dans cette université et coordinatrice de ce programme de formation continue. Formation continue, donc, c'est former tout au long de la vie, pas seulement à 20 ans, pas seulement à la fin du secondaire 2, quand on termine l'école et on s'inscrit dans une faculté, mais c'est former aussi après, quand on a déjà choisi une profession et l'on souhaite approfondir une discipline, un sujet, une langue, obtenir un diplôme pour s'orienter vers une nouvelle profession. L'Université de Genève propose une palette ample et intéressante de choix pour ceux qui souhaitent suivre un programme, même après être rentrés dans le monde du travail. La formation que je coordonne a ouvert ses portes en 2007. Depuis, nous accueillons environ 100 étudiants chaque année pour les modules orientés langue italienne et pour les autres modules de culture et société. Et là, j'ouvre une parenthèse. Nous choisissons pour nos modules en général des sujets d'histoire, d'art, de littérature, de théâtre, de cinéma, avec environ 12-15 conférences ouvertes à tout public, avec des invités du monde académique et scientifique, des écrivains, des artistes, des galeristes, etc. Ce soir, le sujet est différent. Nous sommes d'une part plutôt sur un versant scientifique, ce qui est nouveau pour nous, mais certainement pas nouveau pour cette université. Nous écouterons 3 intervenants d'exception parler d'un sujet d'un très grand intérêt. Nous parlerons avec nos invités de la recherche dans l'espace. D'autre part, ce soir, nous offrons une ouverture à un public non italophone, car la soirée sera en anglais. Et avant de donner la parole à mon collègue Norberto Cioffi, qui nous présentera nos invités, je vous remercie déjà pour votre présence. Vous êtes nombreux et cela fait toujours plaisir. Je vous souhaite de profiter au mieux de cette conférence qui nous portera à lever les yeux vers le ciel et encore plus haut vers l'espace. Je vous remercie.
Good evening to all. I'm trying to wait the screen. Okay, thank you. My name is Norberto. I'm really glad you are here. I'm just going to take you 3 minutes to introduce you to the topic of this conference. If it works. Okay, thank you. Firstly, let me thank a lot of institutions, people, and organizations that helped us to put this event in place. They are here, so again, my thank you to them. The title of this conference is divided in 2 parts. The first is Space and Research. And I want to bring you now your attention to the fact that space and research are really in our daily lives. Here I try to pick up an easy and short list of things we see in our daily lives again. Here we have the PET machine that is the result of the fundamental research done at CERN, the defibrillator that is the result of the vital systems used during space missions, the invention of the web developed at CERN. This is an aerogel material that we use to isolate our houses and is the result of the engineering systems done for a space shuttle. This is the zoom technology we are used to see during sport events that normally has been developed to observe stars, galaxies, and planets. And finally, I like this one. It's a material we use to decorate our places, our houses, but that has been developed to reduce energy consumption on the space stations. So the concept is pretty easy and clear, even if we don't know, we touch on a daily basis space fundamental research. And then really the second part of this conference, which future for the coming generations? And honestly, I don't really have any idea of what it could be. But today we have the privilege to have three people that are at the forefront of the fundamental research, space, and technology. Professor Amalia Ercoli-Finzi from Polytechnic of Milan, Professor Guido Tonelli from CERN, and European astronaut Luca Parmitano from the European Space Agency. So today we are going to listen to them, and we will try together to imagine what could be our future. I'm done, but I want to leave you with this little sentence that I found really appropriate for this event. Let's say there is nothing like a dream to create the future. It's done by Victor Hugo. I hope that tonight, when we will leave this event, all of us will have a dream to shape our future. Again, thank you. After the speeches of our guests, we are going to open a 30-40 minute session of question and answers, and I hope you will enjoy it. Again, thank you.
I think the physics problem is absolutely magnificent, and there is plenty, the thing that I like, there's plenty of room for new ideas. Pretty sure that the exploration of this new energy regime will change in depth our current vision of matter and the universe, and we don't know in which direction.
Good afternoon, everybody. It was a surprise for me. I was not expecting this short movie. I'll try to guide you quickly through a short journey. It's a journey which is quite familiar for high-energy physicists, but you will hear something that will sound familiar also to you. It's a special journey. It's a journey back in time. Actually, it's a journey toward a no place and no time, toward a place, a very special place, in which there was still no place and no time, so at the beginning of our universe. Change it. The question is the question, I used the picture of my granddaughter, Elena. It's a beautiful summer sky. You take a look and you ask the most natural question, which is, well, what is the origin of this beauty? From where does it come? In particular, this universe of matter to which we belong. What is the origin? What is the fate? Is a basic question that every generation asks himself or herself, since millennia, basically. And to answer the question, we need to go through a very special journey. I use this slide with an old ship, because it resembles the adventure journeys to discover new continents or new lands. And actually, we are trying to organize this spatial journey towards the origin of the universe. If you want to understand the origin of the universe, you have to go back in time, at the beginning of the universe, because the universe in which we live today is very old and very cold. It was born in a completely different state, very hot, and a lot of time ago. So you have to go back to these conditions if you want to understand something of the origin of this special object. And you can do it through two basically paths that I call the two roads to knowledge. One is the path that we use, which is the accelerator. This is an image of LHC. You have to consider the accelerator as super microscopes. We look deeply into matter. We take a look to matter, making collisions between components of matter, because we want to understand particles produced at the beginning of the universe. And you are able to produce them using the energy of the accelerator, and you can study them. So we study matter as it was at the beginning, at the very beginning of the universe. But there is another option, which is the options used that we call with super telescopes. So you take a look directly to the large structures. You take a look to the galaxies or the clusters of galaxies, and then you can even imagine what would be the evolution of these galaxies. You can produce models describing what you observe. So the two different paths are completely complementary. Using super telescope, in some sense, you observe objects which are far away. Consider light as a fixed speed. No? The speed of light, you know, is very well known by everybody, is fixed. So if you observe a very distant object, you observe the object as it was at the time in which the light was emitted. So the object is very far, and you observe an object as it was a lot of years ago, many millions of years ago, many billions of years ago. So you have the possibility to observe directly some of the major structures of the universe as they were during the evolution. So the two, combining together the two informations, looking at particles that were abundant in the early universe and studying the properties of these particles and combining this information with the evolution of the large structures that you observe through the telescopes, you are able to produce an image, an idea, a model, a theory about the origin of the universe. And this is what we have put together in the last 100 years, maybe 200 years. This is the idea that we have today of the evolution of our universe. And if you take a look, it is a very old structure, 13.8 billion years. It started from a point, from an anomaly. We are all sons of an anomaly. A particular anomaly in what we call the vacuum state. Vacuum fluctuates. One particular fluctuation was incredibly anomalous. And from this anomalous fluctuation, everything started. We have not understood exactly the mechanism of this anomaly. We call this, the evolution of this anomaly, Big Bang and inflation. A microscopic object fluctuating on a microscopic scale has become immediately, in a matter of a fraction of a second, a macroscopic structure, which is 1,000 times smaller than the universe today, but still an enormous structure. This is one of the most important questions that we are still open today. And then there has been an evolution. Then light has appeared. It was not immediate. Light has appeared after 380,000 years. So the light was there, but it took a while. And then we had the formation of stars. It took about 400 million years to produce the first stars. And then from this evolution, we can explain a lot of the evolution of the following evolution at the point in which we can even understand ourselves. And then you take a look to the fact that this tube has a dimension which grows. And it grows because there is an expansion. This is something completely unexpected that appears in the measurements 20 years ago or so. So what we call today, we call a sort of anti-gravity or dark energy. In a naive idea, the Big Bang expansion would have been limited by gravity. Gravity is an attractive force. So the universe expands up to the point in which gravity starts prevailing on the force of the, let's call it explosion. It's not an explosion, but let's call it naively like this. At a certain point, we have discovered that everything is accelerating. So the speed at which everything moves with respect to all the rest of the universe increases with time. So there is something pushing everything away. Is a form of energy? Is a property of space? We don't know. We don't know exactly. We call it dark energy. It's one of the major questions we are facing today. And one could question what happens on the microscopic scale, because the progress with the super microscopes have been incredibly fast in the last 100 years. And this is the picture of matter. So we have been able to produce elementary particles, the components of matter, of everything, of galaxies, of ourselves, of the TV screen, of everything. And we know that this matter is made out of these basic components, which are 12 particles, leptons and quarks, that interact through other particles. They exchange the forces, the major forces, interacting, exchanging, using other particles. And these other particles are particles carrying the strong interaction, which is the interaction keeping together, for example, the protons in a nuclei, the electromagnetic force, the photons that are circulating in this room, producing the light or producing the amplification of the voice. Gravitational force, the graviton, not yet discovered. The weak force, responsible of the beta decay, an elusive phenomenon that we have been able to explain. This picture we call the Standard Model. And it was developed in the 60s with a lot of experimental measurements and a lot of theoretical progress, but there was, up to a few years ago, a major issue, a major problem. As it happens quite frequently, there is a detail that we have to explain. We don't have yet an explanation. There are different theories trying to explain the detail until we discover in matter the experimental proof that one of these theories is correct. The detail was I might come back maybe to this, that these two forces, let's say the basement of the Standard Model is that these two forces, the electromagnetic force and the weak force, are basically the same force. So the basic of the theory was that these two forces were actually two different manifestations of the same force. Actually, physicists call it electroweak force. Electromagnetic and weak, electroweak. But how would it have been possible? I like this cartoon because there is a sumo player that might weigh 200 kilograms, confronting a girl or a boy maybe weighing 20 kilograms. No? And this is exactly the puzzle. How could it be, this was the detail, that the weak force is carried by the extremely massive W and Z, particles that we have discovered at CERN, Carlo Rubbia, 1984, and they carry the same interaction of the massless photon. The same force is carried by two extremely heavy objects, the sumo player, and the electromagnetic interaction is carried, the same force, by the massless particle, the boy confronting the sumo. And the question was, what is exactly the mass? This was the question. No? Behind this, we have to understand better what gives mass to particles and makes particles very massive on one side or massless on the other side. And there were many different theories trying to explain it. And these three, we are discussing today young generation role. These three youngsters in the 30s, you can see from the picture that I took from that time, it was 1964. And already you can see the different characters. No? The very happy and joking, these two Belgian physicists, while this one that is a British, you see from the attitude that are completely different character, the way in which they dress, or they take a picture. But anyway, these three gentlemen in their 30s, remember this, in their 30s, they produced a theory that was considered completely incredible. Basically, they produced a solution to this puzzle. And the solution at the beginning was ignored by everybody because it was not considered really a viable solution. It was a completely crazy idea. The difference between these two interactions comes from the fact that the vacuum is full of something. So the two interactions becomes different, the weak interaction and the electromagnetic interaction. They are described by the same formula, the same formalism that we call the Lagrangian. So the same formula describes the same interaction. What makes the difference is the vacuum. It appears to be a completely crazy idea because they imagine the vacuum full of everything, full of something. The vacuum not anymore empty. The entire vacuum, including the farthest corner of the universe. It was a completely crazy idea and it was ignored for a few years. There were many other proposals, but at a certain moment, experimental data started becoming consistent with this theory. And this theory was considered seriously by physicists, and they started looking for the particle responsible of making the vacuum not empty. So the theory was elegant and nice, but to be true, we should find something, the particle responsible for producing this mechanism. And this particle was called, since a few years later, the Higgs boson. And it's a story of a mission impossible because basically a generation of scientists tried to discover this particle for decades. And it's the story of an effort that continues from one generation to the other, up to the point in which another generation of young scientists and engineers decided to build this marvel of technology, another crazy enterprise. I remind you, it was considered absolutely crazy to be able to build an accelerator of 27 kilometers and detectors of this complexity, like the one described you, that you can visit at CERN. But it is the story of many technical challenges, because most of the technologies were not available at the time in which LHC and the detector were conceived. You can see here an example of this technology. You have a dream, you have an idea, and if you want to have this idea realized, you have to push technologies. This is science today. If you don't push the technology at the limit, you'll not be able to test the theories or to see if your idea or your dream could become true. Here you see some of the pictures that were taken. I have no time to describe you in detail how many technical challenges we have tried to face in the machine and in the detector, but I can guarantee you that it has been really a huge effort of more than thousands and thousands of people for 10, 20, 25 years. It shouldn't be a surprise because the challenge was really very, very high. But there is not only technology, it's also the story of deep emotion. You see, the faces, the day in which we had the first collisions. After 20 years, you can imagine, these people spent 20 years of their life to live this moment, the moment in which the accelerator worked and we were convincing ourselves that we might be able to find something. You see from this that it's not a story of technology, it's also a story of deep emotions. And I like this picture. You see me, I am the oldest in the group. We are talking of the young generation. Look at the eyes of these young people surrounding me. No? It's a particular moment in which we have achieved an important goal. Take a look to the eyes, take a look to the differences in gender, in race, in everything. This is science today. It's not only something which is cold, which is technology, which is challenge, it's also something that involves deeply the human factors, the emotions. And then there has been something that I'm sure you know, everybody in this room knows, the discovery of Higgs boson. After all this effort, we have been lucky because we have been able to reach the energy at which we had been able to produce in our accelerator and to discover with our detector this particle that escaped all other attempts of detection for decades. And so we had discovered this fundamental particle, and now we can say we have understood something. We have understood what happened at the beginning of the universe. We are extending our knowledge toward this incredibly complex moment, which is the Big Bang. Now we understand what has happened up to the moment in which basically only 10 to the minus 11, so is 100 of a billionth of a second after the Big Bang. So we know, we can describe nature up to this point. We don't know before, but we can understand or we can say something of what has come afterwards. Basically, at the temperature of this value, this invisible field has occupied every corner of the universe, and it stays there. Now we can say, and it's this field that produces the difference in masses in most of the elementary particles, including the W, the Z, and the photon. So we understand now what we call, in technical terms, the electroweak symmetry breaking. In some sense, we have discovered this thin fabric shaping the universe. Now, we have to change the books in physics. We have to change the idea of mass. We have to change the way in which the fundamental interaction have been described so far. And this has brought to two of the boys of the 64 that now are gentlemen of a certain age. Unfortunately, one of the three died. This is another lesson. Remember, he died 1 year and a half before the discovery. So it was really sad because basically he didn't have, not only, I would say, Nobel Prize is important, but the most important thing was the satisfaction of understanding that he was right. No, he was not even able to have this satisfaction. This is the cruelty of life. This was the Nobel Prize was awarded to the theorist François Englert and Peter Higgs. And now that we know this, the challenge continues. So we are talking of the future. What is the future for younger generation? And from my perspective, we need a new generation of scientists to tackle some of the major questions that are still open. I have tried to summarize them in this cartoon. So the origin of the inflation, this particularly strange moment in which a quantum fluctuation has become everything, should be understood. And we are not yet there. We need a new approach probably to understand this. We need to understand what is the origin of dark matter. We have observed dark matter keeping together galaxies, including ours, including our cluster of galaxies lives in families. And the families are kept together by something which is everywhere, including in this room. We call it dark matter because we don't know exactly what it is, and we are not able to see it. But this explanation should be found. And lastly, what is the origin of this dark energy accelerating everything from everything? Again, we don't know, we have no idea, and we have the need to give some answer to this question. So it is true what was said already a few centuries ago by Isaac Newton. What we know are a few droplets. What we don't know is an ocean. Today, our ignorance is immense. So if I try to answer the question of Elena, my granddaughter, I can only tell her I can barely explain maybe 4 or 5% of what we see around us. 95 or 96% is an obscure thing. We have no idea what is made of. And this is why I conclude with this. We need you, basically. We need a new generation of scientists. We need people that in their 20s or 30s are able to produce new, completely innovative ideas. And they have to produce ideas that we might consider completely crazy, as it happened to us in reverse roles. continuing somehow the work that was done by this scientist from Pisa. I remind you, some of the revolution in technology have been mentioned at the beginning by Norberto Cioffi, but I remind you that nobody would have considered at the time in which this gentleman, Galileo Galilei, started looking at this supernova, that an incredible revolution would have started from what he wrote. He wrote that he was seeing a solar system, a mini solar system around Jupiter, I satelliti Medici, no, they were called at that time. And this was the birth of modernity. It was a completely new situation that started from a scientific discovery, bringing a new approach, a new vision of the world and the universe. My secret hope is that some in this room, maybe stimulated by this presentation, will start thinking and maybe producing ideas that could revolutionize in deep our vision of matter and universe. Thank you very much.
In Kourou, French Guiana, the Rosetta spacecraft set off on a breathtaking mission to rendezvous with a comet.
Ma io quello che sto facendo è ringraziando il Padre Eterno di aver costruito le comete, perché sono una delle cose più belle del mondo.
Mamma come sono piccola, mamma come sono piccola. Ecco, bravo, metti a posto tutto bene. Pronto, possiamo partire. Ecco, allora, dopo la presentazione che ha fatto Tonelli sono veramente un po' spaventata, perché lui ci ha portato in un abisso, in un'enormità di mondi e così via. Io parlo di una cosa piccola piccola come sono le comete, però è tutto quello che so fare. Cosa stai facendo? Ecco, fa danno, guarda che fai danno, sta fermo, non toccare, ecco. Cerchiamo di parlare. Allora,
ti traduco questo che hai detto?
No, non tradurre, tanto okay. io parlo adagio e sono convinta che la gran parte di voi capisce. Lei mi aiuta e quindi andiamo avanti.
Facciamo slide.
Facciamo. Allora, qui noi siamo partiti. Ecco, io ho voluto portarvi un verso che ha scritto Pascoli quando ha assistito al passaggio della cometa di Halley. O tu stella randagia, astro nel verso che cercando vai la via onde uscire dall'universo. E quindi effettivamente quello... Ci vede qualcosa oppure no? Non lo so,
sì,
ho delle difficoltà. Allora, da che parte? Perché non funziona, ragazzi? Aiutami un momentino. Ecco, adesso ci siamo. Ho capito, ci siamo. Allora, perché ci siamo rivolti a vedere le comete? Perché noi dalle comete vogliamo cercare di capire l'origine del sistema solare. Questo non dell'universo, è quello che ci pensa lui. No, l'origine del sistema solare.
Stop. Cosa?
Non ho capito. Sì, traduciamo un momentino. Sì, aspetta un momento.
Slide.
Allora, noi vogliamo capire. Noi vogliamo cercare di indagare qualche cosa sull'origine del sistema solare. In realtà il nostro obiettivo ultimo sarebbe quello di trovare qualche cosa che ha a che fare con gli aminoacidi, i mattoni della vita, e quindi capire come la vita è arrivata sulla Terra. Traduci.
Okay.
Sarà un'avventura.
I'd like to start with a verse from Italian poet Pascoli, who said, "O tu stella randagia," meaning, "Oh, you wandering star that are looking for the origin, looking for the way." And actually, what we want to do is to find the origin of the solar system. The true objective of our mission is to find the first amino acids, that is, the bricks of life.
Posso andare avanti? Sono tornato indietro, abbiate pazienza. C'è qualcosa che non va. Ecco. Oh, ci siamo. Allora, qui ho preso una definizione di cometa che mi è sembrata la più semplice di tutte, ma soprattutto volevo farvi ricordare che le comete hanno di bello la coda. La cosa più bella che hanno è la coda. In generale però le comete non hanno una coda sola, ne hanno più di una, e siccome le diverse code sono fatte da elementi diversi, ecco che si distinguono fra di loro. E qui vi faccio vedere una cattiveria che ha fatto il Sole, perché in questa bellissima cometa che era la Hyakutake, questa qui era con la Hyakutake, in questa cometa che è la cometa di Encke, il Sole a un certo punto interviene e con un'emissione importante le fa perdere la coda, che io considero proprio una cattiveria.
Okay. So I'll give you the most simple definition of a comet, a very small celestial body that often develops a tail. The tail is the most beautiful part of the comet. Comets may have more than one tail, and each tail is made of different elements. Here there is an image of Encke comet, and it's a comet that was played upon a trick of the sun. That is, it lost its tails because of a very powerful coronal mass ejection from the sun.
Allora, I tried to use a tentative to say with my English.
Perfect.
I tried. We had the news of comet very, very long time ago. For instance, this is una incisione, engraving of a comet that is in la civiltà Camuna. Civiltà Camuna, that means 70.000 anni fa.
70,000 years.
Vabbè, proviamo. Però, ecco, chi ha parlato, sottolineo italiano, chi ha parlato delle comete, esatto, sono stati molti, ma io voglio ricordarvene uno solo, che era l'almanacco perpetuo di Rutilio Benincasa. Rutilio Benincasa era un astrologo, quindi lui si occupava di astronomia, ma anche di astrologia e così via. Quindi era una persona di grande competenza, anche se un po' strano. Fermo, non dire niente. No. Allora, io voglio ricordare a voi che Rutilio Benincasa è noto per l'almanacco che ha scritto. E questo almanacco, che si occupa di tante cose, in particolare delle comete, però dà anche una legge per giocare all'otto e vincere. È una legge complicata, bisogna prendere l'anno in cui vivete, togliete 1515, quello che resta dividete per 19. Questo vi serve per trovare la tavola buona dove avere le indicazioni dei numeri da giocare all'otto. Allora, io ho provato. Funziona, quindi vi consiglio casomai di dare un occhio anche a questo. In realtà quello che ha fatto Rutilio Benincasa è fare un elenco delle date di apparizione delle comete e associare ad ogni apparizione una disgrazia. Lui era convinto che le comete portassero male.
Okay. So among the many people in history who spoke about the comets, I'd like to remind Rutilio Benincasa, who is the author of a Perpetual Almanac. He was an astrologist and an astronomer, and among the many things he did, he was making a list of comets. But at the same time, he also published a law that enables you to play lottery and win. And I tried, and it works. It works like that. It's a complex formula. You have to take the year in which you live, subtract 15, divide it by 19, and then you get a good table, the good table of the numbers to play. And I tried it, and it works. Among the other things he did, he also listed the years in which comets would appear. And to each year, he associated bad luck, something, a catastrophe, something happening, the year the comets appeared, because they were considered to be bad luck mongers.
Qui andiamo avanti fino a notte, ma non fa niente. molti astronomi si sono occupati di dare un occhio alle comete, semplicemente guardarle. Io non li ricordo tutti, ma semplicemente la Caroline Herschel, perché era chiamata la signora delle comete. Lei ha proprio scoperto 8 comete. In realtà Caroline Herschel, che era oltretutto una cantante lirica, quindi faceva dell'altro oltre a fare l'astronoma, in realtà Caroline Herschel ha aiutato moltissimo suo fratello, e quindi vedete come si chiama? Va bene, prendete una rappresentazione di quando Herschel ha scoperto Urano, e in realtà lei l'ha aiutato moltissimo.
So among the many astronomers who studied comets, I would like to remind Caroline Herschel. She was an astronomer and a soprano singer, and she was called the Lady's Comet, the Lady of Comets. And in this engraving, you can see her with her brother, William Herschel, more famous than she, but she actually helped him a lot in the discovery of Uranus.
Io spero che tutti voi abbiate visto la cometa Lovejoy, l'avete vista?
Io sì.
Vergogna, era bellissima, è una cometa meravigliosa che l'anno scorso nell'ottobre e nel novembre si vedeva magnificamente, e questo vi dà un'idea di perché io amo tanto le comete, che sono veramente una rappresentazione meravigliosa. Facciamo anche l'altra, perché sennò ne abbiamo troppo. Da dove vengono le comete? Fino a 50 anni fa non si aveva idea di quale fosse il pozzo delle comete. Adesso sappiamo che vengono in parte dalla cintura di Kuiper e in gran parte dalla nube di Oort, che però hanno posizioni molto diverse, come vedete in questa rappresentazione, perché la cintura di Kuiper è vicino a noi, poco dopo Giove, quindi in realtà la si trova, mentre invece la nube di Oort è veramente lontana. Noi dobbiamo pensare che vengano da una nube perché non hanno direzione privilegiata, quindi una gran parte arriva nell'ambito dell'eclittica, ma una gran parte arriva senza direzione privilegiata.
Okay, the slide before was a very beautiful comet that could be visible even last year, and the beauty of this image is one of the reasons why she loves comets. In the slide here, the question is, where is the well of comets? Where do they come from? There are 2 main locations that we know about, the Kuiper's belt and the Oort cloud. The Oort cloud is extremely far away, and the reason for not being able to actually say where do they really come from is they have no real direction. Many comes from the ecliptic, but many comets come from any direction.
Allora, a un certo punto abbiamo deciso di fare delle missioni per andare a indagare qualche cosa delle comete. La prima missione che abbiamo fatto è stata quella del 1978. In realtà era un'altra missione, doveva essere una missione fatta per esplorare la zona compresa fra il Sole e la Terra, zona delicatissima per quella che riguarda il comportamento poi della Terra. E quindi siamo partiti con quella. Noi abbiamo fatto la missione e dopo anni la missione continuava ad andare benissimo, non si rompeva mai. Noi facciamo dei satelliti che sono troppo buoni, non muoiono, a un certo punto dobbiamo abbatterli. Allora abbiamo deciso di riconvertirla e con quel poco di combustibile che avevamo ancora abbiamo deciso di far fare queste orbite. Voi vedete che partiamo da questo anello da cui siamo partiti, quell'anello di sinistra, e poi abbiamo fatto tutta questa serie di orbite. Bene, con questa serie di orbite noi abbiamo intercettato per la prima volta la coda di una cometa, che era quella della Giacobini-Zinner. Intanto che c'eravamo, abbiamo dato un occhio anche alla cometa di Halley.
So one of the first missions was in 1978. Its initial objective, its actual objective, was exploring the space between Earth and the Sun. The satellite worked so well that either we destroyed it or we continued, and we decided to keep going. So we reconverted the mission, because we had enough fuel, to study comets, and we did many different orbits, and we studied the tail of a Giacobini-Zinner comet.
Ecco che ho citato Halley, perché Halley ha dato il suo nome a una cometa. Per la verità gliel'hanno dato i posteri e non è che l'ha chiamata lui. No. Allora, Halley in realtà è stato il primo ammiratore di Newton. È lui che ha pubblicato a sue spese in realtà dopo gli hanno ridato i soldi, però a sue spese. Lui ha pubblicato i Principia Philosophiae Naturalis e quindi ha studiato a fondo le leggi della gravitazione universale di Newton, e quindi, capendo che le comete fanno parte dei tanti corpi celesti del nostro sistema solare, dovevano obbedire alle stesse leggi che non i pianeti. Ragion per cui lui ha previsto il passaggio della cometa che poi è stata chiamata cometa di Halley proprio per questo. Quando la cometa è passata, Halley era già morto, ma lui previde che sarebbe passata nel 1758. E nel 1758 gli astronomi hanno incominciato a guardare il cielo. Febbraio, marzo, arrivano a settembre, ottobre e la cometa non compare. La cometa è comparsa la notte di Natale del 1758. Questo è bellissimo.
So this is the story of Edmund Halley, who gave his name to a comet. Actually, the people after him named the comet after him. He was a very strong admirer of Isaac Newton. He published at his own expense the Principia of Newton. Then they gave the money back to him. And he started studying very, very precisely the gravitational law of Newton. So he understood that also comets obey to this law as well as planets. And that's why he was able to predict the transit of a comet in the year 1758, a year when he was already dead, but the prediction was quite accurate. Astronomers started looking up in the sky for this comet at the beginning of the year, and they found it on the 25th of December, the day of Christmas of that year, as predicted.
Noi abbiamo tracce della cometa di Halley nella storia perché è associata alla battaglia di Hastings, quella in cui Guglielmo il Conquistatore in realtà era Guglielmo il Bastardo, ma poi l'hanno chiamato Guglielmo il Conquistatore perché era il figlio di una serva, no? E quindi lo chiamavano così. Allora, lui ha vinto in battaglia invece Harold il Sassone, che era per la conquista dell'Inghilterra. Allora c'è questo arazzo che vale la pena di andare a vedere, io sono andata a vedere, costa ma vale la pena, in cui si vede il re Harold che parla con un cortigiano e sopra in alto, sopra questa specie di torre, si vede la cometa, che è proprio una cometa, perché come vedete non è quella che dipingono i bambini, ma è una cometa vera, che l'hanno vista, insomma. Allora, lì c'è una scritta che dice Isti Mirant Stella, che ha dentro due errori. Non è una stella, e poi se dovevano scrivere in latino, dovevano mettere in accusativo Isti Mirant Stellam. Allora vado avanti anche col pezzettino che c'è dopo. A Padova, andate a vederla, l'adorazione dei magi, cioè il ciclo della vita di Gesù che è stato dipinto da Giotto, nell'adorazione dei magi si vede la cometa. In realtà è una leggenda che quella della nascita di Gesù bambino sia associata a una cometa. Non era una cometa, era una congiunzione di due pianeti che quindi interpretavano come cometa. Però Giotto ha dipinto la cometa perché anche Giotto ha visto la cometa di Halley.
Okay, these are two historical pieces of art where you can see comets. The first one is a tapestry of Bayeux that depicts Harold the Saxon, a king that was then defeated by William the Conqueror or William the Bastard. And it depicts this king, and you can see very clearly a comet on the top of the tapestry. There is a mistake in the Latin writing. They don't use correctly the grammar, the Latin grammar. And then in the other piece of art is by Giotto. You can admire it in Padova in the Cappella degli Scrovegni, and it's the adoration of the kings. There is a comet. It's a legend because actually at the time of the birth of Christ, it was a conjunction of planets and not a comet. But Giotto was an admirer of comets because he witnessed the appearance of the Halley comet himself.
Allora noi abbiamo deciso di andare a vederla più da vicino, la cometa, e l'Europa ha fatto la missione Giotto, che si chiama Giotto proprio per quello che vi dicevo prima, in cui siamo andati vicino al nucleo. Volevamo arrivare a 500 chilometri di distanza, in realtà a 596 si è rotto qualche cosa, ha perso l'assetto, non si è rotto quasi niente, ma ha perso l'assetto. Devo dire che il successo della missione Giotto è dovuto anche ai tanti satelliti che c'erano intorno, tra cui Vega e gli altri satelliti che c'erano, perché a un certo punto abbiamo perso lo spacecraft. Ma con l'aiuto degli altri satelliti l'abbiamo recuperato e siamo riusciti ad andare vicino. Allora, guardate, questo è il nucleo della cometa. Così bello? No. Il nucleo della cometa è questo, nero come il carbone, perché l'albedo del nucleo della cometa è bassissimo. Quindi la cometa è fatta di ghiaccio ed è sporca.
Okay. So we entitled our first mission to find a comet Giotto, and you can see here we wanted to reach 500 kilometers from the comet, but we went very close to that because the spacecraft lost its position. We had lost it even before. We recovered it thanks to the satellites around, the Vega satellite, for instance, and we could see the nucleus of the comet. You can see it's very black and very dirty, because it has a low albedo.
Abbiamo fatto, adesso salto un po' perché se no Norberto impieghiamo troppo tempo, abbiamo fatto un'altra missione come questa, ecco ve la lascio andare, ma una che interessante di missioni è stata questa Stardust, raccolta di polvere di stelle, in cui con un pentolino siamo passati nella coda della cometa e abbiamo raccolto la polvere che c'era nella cometa. Allora, il problema di questa missione, che è andata benissimo, non è stato tanto raccogliere la polvere, quanto piuttosto l'atterraggio, il ritorno a terra. Perché? Perché pochissimo tempo prima era atterrata a terra la missione Genesis, che portava una capsula. Si erano sbagliati a montare il sistema di frenata e quindi invece di frenare all'ultimo hanno accelerato, è venuta giù come un ferro da stiro e si è rotta tutta. Non tutta, perché in realtà è caduta nella melma. È caduta nella merda, è verissimo, proprio così. Ragion per cui qualche cosa si è salvato. Invece noi avevamo montato giusto il nostro sistema di frenatura e quindi non abbiamo avuto problemi.
Okay, this is the Stardust mission. We collected interstellar dust with a pen near a comet. It was a very successful mission. We had just a little problem with the landing back on Earth, but it was all in all successful. A previous mission called Genesis, the capsule, instead of braking during descent, accelerated and it ended up in the mud.
Stardust l'abbiamo già vista, sì. Ecco, sì, niente, non vogliamo più niente. Poi invece gli americani hanno fatto Deep Impact, che secondo me è una cosa spaventosa perché siamo andati a fare danno. Noi abbiamo fatto un buco su una cometa grande come un campo di calcio e vi faccio vedere qui l'avvicinamento, abbiamo un impactor, questa è fotografia di quando c'è stato l'impatto e adesso venite con me che scendiamo sulla cometa, queste sono proprio le fotografie, ecco. Stiamo scendendo sulla cometa e ci siamo sopra.
That was the descent of the Deep Impact probe on the comet. American mission, very big damage. They made a big hole as big as a football field on the surface of the comet.
Allora, abbiamo deciso allora di andare ancora oltre. Stavolta volevamo andare su una cometa e scendere sulla cometa, scendere sul nucleo, visto che avevamo capito che questo nucleo c'era e che poteva tenerci. Abbiamo scelto, non noi, ci hanno imposto di usare la Churyumov-Gerasimenko come cometa perché in realtà noi dovevamo lanciare un anno prima. Lo dico perché ho partecipato alla progettazione, no, di questa operazione. Dovevamo lanciare un anno prima, ma c'era stato un problema col lanciatore europeo. Abbiamo detto cambiamo lanciatore, non si può, non si deve fare perché è una missione europea, bisogna lanciare con un lanciatore europeo e a questo punto la cometa nostra se n'era andata, per una cometa bella, una cometa bellissima, e ci hanno dato invece questa che in realtà è una cometa che sta all'interno dell'orbita di Giove.
So now we're talking about the Rosetta mission. I took part myself in the project of this mission, and it's a way to go beyond with Rosetta. Instead of just just making a hole on a comet. We really wanted to descend on it, land on it. They assigned a comet to us, the Churyumov-Gerasimenko. I say they assigned because the comet we wanted was another one, but because the launcher, the European launcher, was not ready, we needed to wait another year. But the comet doesn't wait, so the comet went away and we had to change comet.
La ragione di chiamarla Rosetta era perché la stella di Rosetta è stato il vocabolario che ci ha consentito di capire i geroglifici. Rosetta sarà il vocabolario che ci consente di capire l'origine dell'universo. Allora passiamo addirittura a un'altra, ecco, così non vi faccio vedere. Ecco, questa vi dà le dimensioni, vi dà un'idea di come si fa. Non è un grande spacecraft. Sinceramente, se lo guardate rispetto alle dimensioni di una persona, alle dimensioni oneste, dimensioni piccoline, in realtà quello che è enorme sono le ali. Noi abbiamo deciso di usare l'energia pulita, niente nucleare, e quindi abbiamo dovuto mettere queste ali che sono 32 metri di lunghezza per 64 metri quadri di dimensione, e con questa abbiamo fatto tutte le manovre, la gran parte delle manovre, e soprattutto abbiamo alimentato tutti gli esperimenti. Vai.
Okay, the name comes from... No, it's okay. The name comes from the Rosetta Stone because we wanted our mission to be the vocabulary of the universe. That was the purpose. The Rosetta spacecraft as such is not that big. It's quite a human size. What is really enormous are its wings, because we didn't want to use nuclear energy. We wanted to use clean energy. So the wings are 32 meters and a total of 64 square meters.
Allora, qui ve le faccio vedere impacchettate, costruite in Italia, no? Impacchettate e dispiegate opportunamente, e le vedete qui confrontate con le persone, sono veramente enormi. Ma uno si domanda, questo bel allineamento perfetto nello spazio c'è? C'è, signori, guardate, questa è una fotografia. Questo è il pannello che, come vedete, è perfettamente allineato. Siamo bravi.
So here you can see the size of the solar panel. They're really huge. The big question was, will they deploy and open in space and be correctly aligned? And yes, indeed they did, because we are very good at that.
Abbiamo fatto un viaggio di 10 anni perché non si poteva arrivare prima alla cometa. Il problema nostro non era intercettare la cometa. Il problema nostro era avvicinarci alla cometa con la stessa velocità. Questo è stato il problema, per poter atterrare, no? Come fanno nei circhi quando saltano da un cavallo all'altro. Ecco, noi dovevamo andare vicino alla cometa e poi stendere sulla cometa. Abbiamo fatto questa operazione facendo una serie di attività nel frattempo. Per esempio abbiamo fatto i flyby, 3 della Terra, flyby, ecco, e poi il flyby di Marte. Vi faccio vedere solo quello di Marte perché è il più interessante. Guardatelo qua. Qui si vede uno dei pannelli e sotto c'è Marte, e siamo a una distanza di 250 chilometri, che è la distanza tra Milano e Bologna. Il che vuol dire che se su Marte c'erano le piante, noi gli facevamo il pelo.
Okay. So the mission lasted 10 years because the problem was not just to intercept the comet, but to approach it at the same speed because we wanted to land on it. It's really like wanting to follow a running horse and jump on it. It's quite tough to do that. We did a few flybys. We did the flyby of the Earth. Here you can see the flyby of Mars. We were 250 kilometers from Mars. It's the same distance as Bologna and Milan, so we were really close.
Una cosa interessante che abbiamo fatto, in realtà ce l'hanno fatta fare, è stato vedere anche 2 asteroidi. A me gli asteroidi non piacciono, sono degli stupidi sassi, proprio non vale la pena, uno diverso dall'altro. Però intanto che c'eravamo li abbiamo guardati, e soprattutto guardate questo, che è stato chiamato Lutezia, perché è frutto di un astronomo dilettante che stava a Parigi sopra all'hotel Procop, c'è ancora adesso, no? Andateci a vederlo. Lui aveva una stanzetta sopra, ha fatto un'osservazione, ha visto questo asteroide e l'ha chiamato Lutezia in onore di Parigi.
While we were there, we also decided to look at 2 asteroids. I personally don't like them, they're just ugly stones. And one of the 2 is called Lutetia, because an amateur astronomer discovered it, and he was staying in Paris at the Hotel Le Procop.
Allora, noi siamo andati a guardare abbiamo incominciato a vedere la cometa, eravamo abbastanza vicini. Cometa si chiama Churyumov-Gerasimenko perché scoperta da Svetlana Gerasimenko. Ma lei ha fatto un errore, credeva che fosse un'altra cometa, la Coma Sola, che stavano cercando. È stato Churyumov che si è accorto dell'errore e quindi hanno trovato una nuova cometa, l'hanno chiamata Churyumov-Gerasimenko. E noi ci aspettavamo di trovare quella che Sir Fred Lawrence Whipple ha chiamato la palla di neve sporca. Questo era quello che noi pensavamo di trovare. Guardate che cosa abbiamo trovato. Una cosa è brutta come il peccato mortale, è veramente una cosa indegna, guardatela, più ci andavamo vicino e più ci sembrava brutta. E difatti, guardate, eccola, guardate, le manca la corda e poi è una scamorza. Vedete?
Okay. The name of the comet, Churyumov-Gerasimenko, is due to Svetlana Gerasimenko, who actually thought the comet we were following was another one called Coma Sola, but then Churyumov understood that that was a mistake. That's why the comet has the double name of the two. We expected to find something that Fred Lawrence Whipple had anticipated, dirty snowball. But what we actually saw was quite disappointing, a very ugly stone. Look at it, just put a piece of rope around its neck and it's like a dried mozzarella.
Allora, qui ci siamo avvicinati con queste orbite triangolari, che dico, parlare di orbite triangolari ci deve essere Keplero che si sente morire, no? In realtà non sono orbite triangolari, sono iperbole molto molto aperte che noi consideriamo come lineari tra un punto e l'altro. Ma il problema non era questo. Siamo scesi sulla cometa e ci siamo scesi con questo lander che si chiama Philae in omaggio di, ecco andiamo a vederlo, in omaggio di questo, come si chiama? Obelisco, questo obelisco che sta a Londra nel giardino di questo lord che l'ha fatto trasportare. Io sono andata a vederlo, 29 sterline per vederlo, è un po' tanto, però vale la pena di vederlo. Allora, mi fa piacere di ricordare che è stato trasportato in Inghilterra da un italiano, Giovanni Belzoni, che era un egittologo importantissimo, che non viene assolutamente ricordato, assolutamente. Al British Museum c'è una targhetta piccola così che dice scoperto da Giovanni Belzoni, che tra l'altro ha scoperto la piramide di Chefren e per essere sicuro di che non gli portassero via la scoperta ha lasciato scritto scoperta da Giovanni Belzoni. Ecco. Allora, questo è un particolare, mi piace ricordarlo per dire che la storia poi non ricorda tutti per bene. In realtà voi avete visto che avevo fatto l'elenco degli strumenti che ci sono sul lander, gli strumenti sono 10, in realtà ne ho segnato 9 perché il 10° è il mio, che è arrivato qui sulla cometa, che è un sistema di raccolta di campioni, trivellazione e raccolta di campioni, che come vedete è fatto da un drill e da un sistema di raccolta di campioni per cui i campioni vengono messi in fornetti e qui vengono scaldati per generare i volatili. I volatili non sono gli uccelli, i volatili sono in questo caso i gas che vengono sviluppati.
Okay. So back to the...
Vai.
The comet was being approached by our probe with what we call triangular orbits, which is not a very precise definition. It's actually open hyperboles that we consider linear. It descended with the lander called Philae because we inspired the name from the obelisk of Philae in the Temple of Isis that you can see now in London. It was brought to London by an Italian Egyptologist who did very important things but is quite unknown and not very well remembered. He also discovered a pyramid and he put his name on it just to be remembered. And going back to Philae, I list here 9 instruments. Actually, there were 10. I list only 9 because number 10 was the one we made and we projected. And it was basically a sampler with 26 platinum ovens to collect these volatile samples.
Perfetto, allora, questo è perché abbiamo conservato al Politecnico di Milano lo spare, quello che non è volato, e stiamo lavorandoci sopra per simulare la presenza sulla cometa. A un certo punto ci siamo distaccati. Come vedete, la separazione, quando parlo di separazione, vi ho portato una vecchia slide in cui l'oggetto è chiamato Roland, Rosetta Lander, no? E non File. In realtà, dopo gli abbiamo cambiato nome, perché Roland in francese è Orlando, e Orlando ha fatto una brutta fine, allora noi volevamo essere sicuri invece che avrebbe fatto una buona fine. Ci siamo distaccati e abbiamo scelto la zona dove scendere, il famoso sito J. Io sto cercando di radunare, tagliamo, vedi che sto tagliando.
So the slide before was the ST2 facility at the Milan Polytechnic, where they have the spare to simulate every operation. So then there was separation. The probe was initially called Roland, which means Rosetta Lander, but in French it means Orlando, which is a bad luck name because he ended up badly. So that's why we renamed it. And that's the descent.
Ci siamo? Fantastico. Andando velocissimo. E siamo scesi sulla cometa. Questa è una simulazione, quella che l'ESA manda in giro e che sono così belle. In realtà a me non interessa la simulazione, mi interessano le fotografie. Allora, questo è il distacco. Questa è la fotografia del pannello, lo vedete sopra il pannello dell'orbiter che è rimasto in orbita, che viene fotografato da File che si è distaccato. Questa invece è la fotografia che l'orbiter ha fatto di File quando stava scendendo, che per noi è importantissima perché si erano aperte le zampe. Questa è una cosa che dobbiamo verificare. E queste sono una serie di fotografie che insieme descrivono la traiettoria. Però sono fotografie e ci siamo avvicinati al nostro sito finale. Vai, ce la fai tu.
Yes. First there was a little clip by ESA. It's just a simulation. I don't like simulations, I prefer photos, and she's shown a few photos of the separation, photos done by File itself of the panel and of the orbiter.
Questa è la fotografia che... Si è sentito qualcosa? Questa è la fotografia che abbiamo preso quando abbiamo toccato terra, abbiamo toccato suolo. E là in cima, se avesse funzionato, proviamo di nuovo, torno indietro, proviamo di nuovo a vedere se magari... Si dovrebbe sentire il touch. No, niente, non c'entra, niente. Noi abbiamo il rumore, in realtà non abbiamo sentito il rumore perché sulla cometa non c'è atmosfera, quindi non si sente suono, ma abbiamo convertito le vibrazioni in suono e quindi è come se avessimo sentito il touch della cometa. Siamo arrivati a terra e questo è il momento in cui siamo scesi. La prima fotografia a sinistra è 5 minuti prima dell'atterraggio. Come vedete c'è il cerchio rosso e dentro non c'è niente. La seconda è 5 minuti dopo l'atterraggio e come vedete all'interno del cerchio rosso c'è una traccia di qualcosa che è il nostro File che è atterrato. Quello sotto il punto verde era il punto di discesa nominale, che in realtà noi siamo atterrati a 100 metri di distanza con l'errore di un secondo. Allora, siccome eravamo a 500 milioni di chilometri di distanza dal Sole, vorrei un applauso.
So in the slide before there was a touchdown. We actually heard the lander touching down, not because we really heard the noise, because you can't hear any noise in space, but we converted the vibrations into sound. Then there are 3 photos of the landing. The first on the left is 5 minutes before the landing. You can see the red circle with nothing inside. Then the second one is 5 minutes after the landing. You can see the red circle with the dot inside, which is Philae, the red dot. And the third one was the nominal descent point. It's green. The nominal descent point was 100 meters. We reached it with a 1 second delay, and we were 500 million kilometers from the sun, so I deserve an applause.
Allora, cos'è successo la sera prima? Torniamo indietro di uno. Cos'è successo la sera prima dell'arrivo, che era il 12 di novembre? Abbiamo scelto il 12 e non 13 proprio sempre per quella ragione. Allora, mi arriva questo messaggio. Nell'ipotesi che vi chieda qualche cosa, succeda qualche cosa, voi date il numero dell'ESA, non rispondete, non dite niente. Se ce lo dite voi, vuol dire che erano preoccupati. E difatti, allora io mi sono messa a pregare, qualcun altro cercava un po' di fortuna sempre con questa idea. E difatti che cosa è successo? Ah no, ho sbagliato, scusate. Che cosa è successo? Il distacco è stato ottimo, nominale. La discesa è stata nominale. L'accometaggio è stato nominale. Che cosa non ha funzionato? Il sistema che doveva controllare, mantenere a terra il lander una volta arrivato a terra, quindi doveva premerlo sulla cometa, gli arpioni che erano stati messi sulla cosa, e anche le fotografie che siamo riusciti a prenderne una sola.
Okay. So the day before the detachment, the separation of the lander was the 12th of November. We chose that date not to fall on the 13th, which brings back luck. We received a very strange message from ESA asking us that if there was a lander crisis situation, we should not answer the phone, we should provide the phone of ESA. So everybody got worried. I started praying. And then the day arrived, the separation was nominal, the descent was nominal, the landing site was even more than nominal. What did not work was the system that was supposed to catch the lander on the comet. The harpoons were not fired, and the camera took only one image, the one that you see there.
Ecco qua, ci sono. Perché non funziona più? Eccolo qua. Non hanno funzionato gli arpioni. Gli arpioni ne vedete uno che sta lì in mezzo sotto la cosa, quello che dovrebbe. L'arpione è una cosa fatta così, sono proprio quelli che usano come in montagna, no? Voi lanciate un arpione, l'arpione entra nella terra, nella roccia, ha queste alette che cercate di tirarlo fuori, ha queste alette che gli impediscono di essere tirato fuori, riavvolgete il cavo che lui si era portato dietro e a questo punto lo bloccate. Non hanno funzionato. Mi permetto di dire, e ci tengo, che è stato fatto dal Max Planck Institute, la signora Merkel, insomma, ecco questo.
So why did the harpoons not work? They actually are constructed like the same equipment you use in the mountains, with wings that you throw on the soil, and they get grabbing the soil, and then they rewind with a piece of rope, and then they block. It didn't work, and I would like to say that it was made by the Max Planck Institute in Germany.
Allora, invece di atterrare una volta, siamo atterrati 3 volte. Cioè abbiamo fatto un primo balzo, un secondo balzo e al terzo ci siamo fermati. Più avanti, adesso chiuso perché ci abbiamo già parlato anche troppo. Qui abbiamo la dimostrazione che abbiamo toccato 3 volte terra e dove siamo andati a finire? Ecco dove siamo andati. Aspetta un momento, com'è che non viene più? Allora, eccola qua. Torno indietro, scusate. Sono un po' una pasticciona. Ecco qua. Allora, questa è la fotografia che abbiamo preso quando eravamo a terra. Ma il fatto è che non eravamo nel campo di vista di Civa che ha preso la fotografia, ragion per cui l'unica cosa che abbiamo fotografato è stata una zampa. Questa è una delle 3 zampe che dovevano essere. Dove siamo non lo sappiamo ancora adesso, anzi la mia idea è che ci stiamo muovendo sulla cometa, perché noi sulla cometa, noi siamo 100 kg, ma sulla cometa pesiamo come un foglio di carta velina.
So when we landed, we jumped 3 times. We made 3 jumps. At the 3rd jump, we stopped. There is proof of it, the graphic on the slide before. And the next one is the photo of the landing. We are not in the visual field of the camera, so you can only see one of the 3 legs. And according to me, we are still moving around on the comet surface, because even if the philae weighs 100 kilo, actually up there it's like a plume. So for sure it's still jumping around on the surface.
Noi avevamo una batteria che poteva, non è importante questo, una batteria che era carica, ci siamo portati la batteria primaria carica, e con quella abbiamo lavorato per 62 ore. Tutti gli strumenti che erano su file hanno lavorato per 62 ore. Poi la batteria, compreso il mio, poi la batteria si è spenta e adesso stiamo cercando di capire qualche cosa. Questo non ve lo faccio vedere perché oramai è troppo noioso, ma il problema è questo: abbiamo fatto tutte le operazioni disponibili, ma in 62 ore noi abbiamo fatto tutte le operazioni che avevamo preparato in 10 anni. E questa, guardate, questo è un messaggio per i giovani. Guardate quanta gente giovane ha lavorato solo per file, il che vuol dire che anche noi vecchi, ma soprattutto i giovani, se vogliono, possono ottenere qualunque risultato. Grazie. Abbiamo finito.
Okay, so we started with a loaded battery, a charged battery, could work for 62 hours. It did work for 62 hours, and we actually did everything that was planned to do. We did everything that was planned to do in 10 years, and we executed it in 62 hours. The last photo is the group of philae, and you can see a lot of young people, and this means that young people, when they want, can get where they want to go.
Grazie, grazie, grazie davvero, grazie.
In the meantime, we are waiting for Luca to load the presentation. Let me really thank you, Paola Catapano from CERN, for the live translation.
Oh, it was a pleasure.
No. This one. It's kind of fixed behind this thing. I'm not used to talk from behind the desk because I'm shy, so I'd rather be in the front. Amalia, I have to say that you probably ruined cheese for me forever. Every time I'm going to look at a scamorza now, I'm going to think about ugly stones flying in space. My future has changed forever. But thank you, it was wonderful. I really am, a bind here because following such amazing presentation, it's definitely hard. It's me. It's definitely hard for me now to try and come up with something as interesting. The theme of the presentation, the theme of tonight's conference is the future, and science and future. Science, research, future, they're all connected, and hopefully with my presentation, which is really a video that I will show you, I will try to make a connection between research, space research, and future. Perfect. So, this is a standard video that I always show anytime I have conferences, so you're not very special tonight. However, I will try to make the content special, specific for tonight. I have the honor of talking to young students, and students are my favorite public, always. And the reason is that I'm talking directly to the future right now. You are the future. I have 2 young daughters. They are also the future. And you have something that even the most accomplished person in the world right now, just go ahead and pause it. He has something right now that the most accomplished person, the most accomplished scientists, engineers, and astrophysics or astronauts, he has something we all envy that we don't have anymore. You have time. Your time is incredibly valuable, and it's all in the future. That's why it's so important. However, like I always tell my daughters, the future doesn't belong to you. It's not for you to do whatever you want. It's in your hands, however, so it's a great responsibility. I really feel this responsibility when I talk to students, and so tonight I would like to maybe pass a little bit of one word that I bring with me every time I talk to students, and that word is inspiration. The inspiration tonight comes from this video, so go ahead and start. It's the story of my expedition, and I will ask Norberto to pause it every now and then so that I can pick up on the main theme, which is the future. So what we were looking here is a piece of future already. It's a rocket. And when I say it's a piece of future, it's because right now, while it's standing, while it's been erected in Kazakhstan, this is the Cosmodrome of Baikonur in Kazakhstan. Right now, it's just a piece of metal, but it has the potential to bring humans in space. So the future, it's all in the happening. I'm going to turn this around and talk from here. Much better. So in this video, you're going to see the launch. This is the Soyuz rocket TMA-09M, which is the one that I flew in. Right now, there are 3 humans. Let's see if I ever... There are 3 humans sitting up here, about 70 meters from the ground. They're thinking about their future. How long is it going to be? Maybe 30 seconds. Hopefully not. But then you have this vibration coming from below. The rocket, the spacecraft comes alive. And when I say alive, it's like a beast. It's a humongous beast breathing and shaking. And it dwarfs you. And it squashes you into your seat with an acceleration about 4 Gs, 4 times your weight. And in 8 minutes and 48 seconds, it takes you from 0 to 250 kilometers, the same altitude of the comet chaser, and from 0 to 28,000 kilometers an hour, 17,500 miles an hour. And then 6 hours later, you are ready to join the space station after 4 orbits. And there it is. This is the space station. This is the screen that we have in our computer. Now, if you want to pause it for a second, when you see that screen, it doesn't look very futuristic, does it? So we are talking about research in future, but that screen doesn't look very futuristic. Well, there is a reason for that. When you are in space, we use technology that needs to keep us alive. And so we like the technology to be very solid. We don't like to use technology that needs to be tested for something that we are going to use. We like to test technology that you are going to use. Not because we don't want it to work. We want it to work really well. But we test the technology of the future. How many among you are engineers here? So there's a few engineers. How many of you want to be astronauts? There is one, good. You have way too much hair to be an astronaut. But your helmet won't fit. So in 20 years, we will go back to the moon, probably. And hopefully in about 30 years, I hope, we will go even further to Mars. Now, the technology that we are testing today, by that time, will become very solid. That is the principle of test flying and experimentation. So today on the space station, we use equipment that to you look like the panel on Darth Vader's costume with the big buttons and the lights. And it's like that because it's technology that comes from 20 years ago or 30 years ago. When I was a kid, I was even younger than you are now. But the technology that we are testing today, oh, that one, it looks like the future. And but in 30 years, it may look old to you, but I will remember how new it was to me. But when you land on the moon and on Mars, that's when you will use it, and it will be solid, it will be experimented, it will be tested. It will be yours to use. Let's go back to my old horse here, to the Soyuz. Go ahead and start the video again. Just to give you an example of how old this technology is, this is a periscope. And when I say a periscope, I mean a piece of lens that moves with a little mechanical motor. And that's what we use right here to check our target. We use a radar. These are radars, very basic radars, that let us connect to the space station. Now imagine 20 years ago when we were flying on Mars, and when we were building the space station 15 years ago, those radars were very innovative. So technology has a strange way of being in the past and in the future at the same time. That's the window from which I would be looking outside if I weren't looking straight ahead to make sure that we were hitting the right target. We didn't want to land like Philae. We wanted to land only once. Here, the entry into the space station is always fantastic. It's an amazing experience. Amalia said that they studied 10 years so that they could land and use those 62 hours on the comet. Well, I waited 33 years from the first time that I said I wanted to be an astronaut. I was about 3 years old, and I was 36 when I entered, so I waited longer. This is my crew. You see, this is crew 36 with my colleagues from all over the world, very international crew. We had 3 Russians, 2 Americans, 1 Italian, and then later on we had also a Japanese. So a very international crew. The beauty of the space station, and this is also something that to me belongs to the future, is that it's incredibly international and everybody works with the same objective, and it's something that I hope for the world also. Now you see that the space station is incredibly big. They always ask me, do you feel claustrophobic? No, I don't, because it's really big. It's as big as an airplane, so it's not like living inside a submarine. This is a warehouse, and also we have such freedom. This is Karen pushing herself with just one piece of hair. See how easy it is. It's an experiment that I couldn't do, obviously, but Karen could. And talking about future, this is something. What we are doing here is also part of the future. We use our equipment in extreme environments. So here, we are in Columbus, the European lab. This is a rack, and I'm repairing a piece of equipment down here. And when I say that we are testing the future, well, we have to know, if we want to go to Mars, and it takes us, right now, it would take us 6 months to fly to Mars. We have to know how long, go ahead and pause it. We have to know how long our equipment can last before we have to change it. Because guess what? If you are on your way to Mars, there is no way to send a piece of equipment back from the Earth. Either you built it on the station, and right now, talking about future, we have 3D printers in orbit with which we are printing small pieces of equipment that we can use to replace failed tubing, failed piping, small parts that are easy enough to repair and don't need strong structural parts. But it's plastic that's being printed on the space station. It's amazing. That's the future. Another thing that I'd like to talk about is this piece of equipment here. And it's the 3rd time this week that I talk about it, because it's incredibly important. It is a mix of past, present, and future. This is the toilet. So, since it's just a container, I would say that that's the past. Even if you show an Egyptian from 3,000 years ago a container and said, this is your toilet, he would probably recognize it. However, it's something universal. We humans have a feces, we have urine, we have to find a way to get rid of it. And this is very basic. We just put it in a container and leave it there. However, I promised you the future. And the future is right here. This is a mix of present and future, as a matter of fact. This is a filter. Chris Cassidy here, my crewmate, is replacing a filter for what we call the WPA, the water process assembly, which also contains the UPA, the urine processing assembly. Those two things are connected because what we do is we drink the coffee in the morning, which is brown. It goes through our body, becomes yellow. Then it goes through this whole system and these filters. It turns transparent again, and a week later we drink it. Now, if you go into Mars and it takes you 6 months, there is no way you can take all the water you need. It's impossible. Water is heavy, it's very dense. 1 liter of water is 1 kilo. And weight is so important to minimize. So I can guarantee you, where is my astronaut? I can guarantee you that when you fly to Mars 20 years from now, with much shorter hair, you will be drinking not only your urine, but everybody else's urine. And it will be something possible. You're drinking dinosaurs' urine anyway on the Earth, so it's nothing different. But you will be using something very similar to this, only possibly much smaller and much more efficient, because right now we are still not recycling 100% of what we drink. We still have to eliminate something. And also, more likely than not, I hope, you will be using whatever is left in this container. You will probably be using it to grow food, hopefully. We are researching, talking about research in future. We are studying now on the ground. There's a site in Spain that belongs to ISA and other places in other institutes. We are trying to find a way to create a closed system where we can recycle everything. And that will be the future. It's the only way that we can imagine landing on a new planet, whether it's the moon or, which is not a planet, to land on a new cosmic object, whether it's a moon, whether it's a planet or an asteroid, as ugly as they are. It's the only way we can imagine to land there and terraform the surface, make it livable for the humans. We have to have a closed environment. So our water will be recycled, our air will be recycled, our feces, our organic waste will be recycled. Go ahead and start again. So this is where science and technology meet together with our needs. This is part of the Russian system. Karen here is showing you her room. So we don't have a lot of space in space. Our rooms are as big as a telephone booth, for those of you who remember what a telephone booth looks like. Not many. Now pause it for a second. Okay. We were talking about research and future. This image behind me, this very short video, showed you a burner. It's a combustion chamber that we have on the space station in the US lab. And it's an amazing piece of equipment because you can imagine that space stations and fire do not go well together. It happened once in the Mir. It didn't go too well. So we don't want to recreate a fire on the space station. However, we have experiments right now that use this combustion chamber to burn. And what do we burn? Well, we burn all kinds of things. We love burning things. We have to be a bit crazy, but we really like to burn things. So we burn different kind of materials to see how they react in burning in zero gravity. And that's an unfortunate experiment that I couldn't do. However, this was part of one of the experiments that we did while I was on the space station. Here, in this experiment by the Italian Space Agency called Green Air, we are burning biofuels. So these are organic fuel created on the ground, not fossil fuel, but biologically. And the experiment was to find a combination that would create the least amount of toxic waste. Now, when we burn something, we always create something toxic at the end. It's inevitable. It's the nature of combustion. But thinking about the future, again, your future, your hands, your time, thinking about that, we want to imagine a future where biofuels that we can recreate without wasting them, leave the air a little bit cleaner, have a less of an imprint that we are doing now. So this is the beginning of that voyage. It's the beginning of that capability, but it starts on the space station. And you may ask me, why don't we do it on the ground? Why do we do it on the space station? Well, we noticed that in orbit, in a zero gravity environment, the shape of the flame and also the combustion itself is a little easier to study. We have less dimensions. We take one dimension away, the gravity. And so it's easier to study, and the results are easier to compute. Now, I don't have the results of that experiment because it only happened a year and a half ago, and science takes its time. But we're talking about the future here, so I thought that was a good subject. Go ahead. So this is actually an experiment where we're burning some kind of material. Talking about future, how many of you like robotics? Where are my engineers? No nerds? No? So robotics is very big in space because we always think about movies like 2001 Space Odyssey, where HAL killed everybody on orbit. And so we are studying the ways to use robots to do our job. So Robonaut is a very dexterous robot that can help us doing EVA. And these two spheres, it's an experiment called Spheres. Go ahead and pause it. That's an interesting story. So how many of you have watched Star Wars? Good. That's the kind of answer that I like. So in the first episode of Star Wars, the original one, in the original Star Wars, Luke Skywalker meets Yoda, and then he trains to become a Jedi. He's got a sword, he's blindfolded, and there's a little robot shooting lasers. Remember that scene? Good. So a professor of MIT that was just as much a fan of Star Wars as I am asked his students to build the robot. And the result is the program, the Spheres program nowadays. And there's going to be soon another one that is even more improved. Now, Spheres, those little robots are an artificial intelligence, not too bright. They maneuver in space in 3 dimensions, and we use them for competitions with students where we ask them to create maneuvers on the ground for them and to see which kind of maneuver in 3D is more efficient. So we've had also some other experiments where we try to see how we can, for example, navigate in 3 dimensions for example, to inspect something outside. Because in case a communication antenna breaks, you don't want to send an astronaut and then lose him in space. Just kind of like a space odyssey. Here's another piece of experiment that's really interesting. In space, because we are free from the gravitational effects, we are still under gravity. Gravity is a universal force, but because we are continuously falling, we are free from gravitational effects. Liquids behave in a very interesting way. They become spheres, and you can also, by changing the shape of the container, you can create movement. So this experiment, which is an experiment on capillarity, which continues until today, deals with that. The capillarity, changing the shape of a container, creates a motion. So imagine if in the future we can have pumps moving liquids from one place to another without using energy. It's a pretty clever way to do things, in my opinion. Go ahead. Yeah, it's not moving really fast, but it's moving. That also matters. Talking about future, here is another part of the science that we do on the space station that concerns future. Here, Karen Nyberg is taking an ultrasound of the spine of Chris Cassidy. Now, until we did this experiment in orbit, we didn't think it was possible to actually get a good image of the spine, but we did. And the image that you saw after that was an ultrasound of the ocular bulb. This is to study, go ahead and pause it. I promise I'm gonna make it faster from now on. But this is it's really the meat of what we do on the space station. It's the study of the physiology. When our friend wants to go to Mars 20 years from now, we are going to have to find a way to prevent his body from degrading, from degenerating. And that's what we're doing on the space station now. We are using our body as testing equipment. We are letting our body degenerate at a faster rate than here on Earth, so that you can go to Mars 20 years from now and get there and land once, not 3 times, and land and still have strong bones, strong muscles, and good eyes. Because right now, when we go in space, if we don't do anything, we come back and we would have a very damaged body. But we've done a lot of research on that, and so we are getting much better, so that in the future we'll be even more capable upon landing. Go ahead. Yeah, not a very clever face in this image. I'm just happy because I'm preparing for an EVA. So what we're seeing here, this is a cable. It's called safety tether. It's a metallic cable that we use on orbit in order to attach ourselves to the space station when we do an EVA. Now, why is that important? Well, it's very important if you've seen the movie Gravity to prevent that from happening. We don't want to get lost in space, because if we do, it's a very bad day, incredibly bad day. So we have a safety tether, kind of like a dog on a leash, so that we would come back to the space station in case something happened. Now, this part of the video is one of my favorite, because even though the spacesuit are certainly not the same spacesuit that you see in the movie The Martian or other sci-fi, these are the suits that we're using now to perform EVAs. And EVAs are amazing. They're fantastic. You go outside in the most dangerous place in the world or out of the world and work. Now, if this is not science fiction, I don't know what is. It's beyond my dreams. And it was amazing to be part of that. This is me coming out in my big Michelin Man suit. And once again, this is part of the future, because when we go to Mars or when we go back to the moon, we will be using something that is going to look very close to this. Hopefully it will be an evolution, but it will be very similar. And we are testing these suits to their limits, because nowadays these suits were created to go to space, perform an EVA, come back to Earth and be refurbished. And we are not doing that. We are pretending that we are on our trip to Mars, and we leave them on the space station, and we refurbish them as much as we can on the space station. And sometimes they fail. So for example, on my second EVA, there I am. On my second EVA, something went wrong. And just as I was saying earlier, when something goes wrong during an extravehicular activity, it's a very bad day. So this is me on my first EVA. You see this backpack. This is the tip of the space station. We're flying at 28,000 an hour in this direction. The backpack is called in English a PLIS, Portable Life Support System. It generates an atmosphere. Can you pause it? Okay, it generates an atmosphere inside the suit. It creates a ventilation so that we can breathe. It also circulates water for a suit that we wear underneath the suit, with lots of little tubes, kilometers of little tubes, to drain the heat out of our body. So, who has seen the movie Gravity? Yeah, okay. So when Sandra Bullock takes off the suit and she's wearing hot pants, that's not accurate. So instead, we have this suit with water circulation. And that day, the system that is in the backpack, there is a pump, a very tiny pump that creates this motion of air and water. That pump failed. And instead of separating the water from the air and generating ventilation in my helmet, it started spraying water inside my helmet. And that's what the simulation is showing, the way the water was flowing over my noggin. Now, on that day, probably if I had hair like your colleague, it would have been much better. But I don't, and so water was flowing over my head, and then go ahead and start it again. And until it started covering my eyes, my ears, and my nose. So I was outside of the space station, completely isolated, and I couldn't see, I couldn't speak, and I couldn't hear. I couldn't really breathe, but only through my mouth, and the water was filling up my helmet. So, yeah, it was a bad day. However, going back, this is the part where they tell me to go back inside. I'm going back inside here, inside the hatch, trying to, this is doing the repressurization, and this is the moment when they bring me inside. Here I am, just like a sack of potatoes, and my helmet is half filled with water. Look at the faces on my crewmates. They were not happy. And then finally, look at all the water flying around. That's water that was attached to my noggin. And this is the effect of the water. You see why I was saying that if I had hair, probably the problem would never have started. But instead, because water becomes like a gelatin, and it stays, go ahead and stop it. And it stays attached to the skin. My daughters loved it when I showed them this trick on the space station. Every time I had a video conference with my daughters, they say, do the water thing with your hair. And I'm like, okay, and I would do the water, spray the water, and then shake my head a little bit. And they called it the water hair. So they're young. So what can I do? What can a father do? So it was a very bad day for me. However, when you go back to that event and translate it into the future, and that's what we're talking about tonight, everything changes. And it was a great day. It was a very good day for space and research for 3 very good reasons. The first reason, my favorite one, is that today I'm here talking about it. So it was a good day because I'm, at least for me. I have to ask my wife about that, but at least for me it was a very good day. The second reason is that the most important is that we found a problem that we didn't think was possible. And that's, again, the same reason why we use those old-looking machines and we use old-looking spacesuits. Well, because we like to know. We don't like surprises. We like to know what kind of problems we can have. And we try to think in advance. But even the best engineer in the world cannot think of something that we have never experienced. We can think of accidents that have happened on other systems that are similar. We can think of airplanes, we can think of cars, trains, we can think of underwater suits, but we cannot think of something that we don't know. So when we built the spacesuits, we didn't think that this accident was possible. We thought that the water would just flow away around the helmet. It would be uncomfortable, but not dangerous. We never thought that it would accumulate in the helmet, covering the head of the astronaut. So that day, we discovered that it's possible. And I can guarantee you that it's never going to happen again, ever. Because now we have systems in place that will prevent that from happening. We have also, in case that system doesn't work, we have a backup system. We have a snorkel that goes inside the suit so that an astronaut can actually breathe from the rest of the suit while the other person brings him inside. But most importantly, we have found a problem that will never happen in the generation of the future. Because right now we are building new spacesuits, and they will be different. They will have other problems, but they will not have this problem. And so we already made a step in the future when my accident happened. And the third reason why it was a good day that day is because we discovered that our training works. Because even though we didn't think that was possible, there was no procedure for this kind of emergency. There was nothing that I could read or nothing they could tell me to do. Well, our training worked anyway because they prepared me for all kinds of evenience. And so when I found myself isolated and blinded, I was still able to navigate, just remembering the structure of the space station after hours and hours and hours, hundreds of hours underwater. I have over 180 hours underwater in a spacesuit identical to that, navigating around the spacecraft. So with my eyes closed, I knew where to put my hands so that I could go back, even in the most dire situations. So, a good day after all. Go ahead and start again. I'm going to try to make it fast, but here is a piece of past that transforms into the future. I like this comparison. This is the ATV, Automated Transfer Vehicle, an amazing machine built in Europe. And it's built in Europe, it's a European technology. Actually, the pressurized module is Italian technology, it's built in Italy. And it's a program that's completed, it doesn't fly anymore. However, the basics of the program will be the service module of the Orion spacecraft. For those of you that know what Orion is, the service module comes directly from there. This is another spacecraft, it's called HTV from Japan, obviously. The Japanese name is Kunotori, which means the white stork. And it's a different technology. While ATV is automated, meaning it docks by itself. And after traveling for millions of kilometers, it docks with the precision of 1 centimeter. So a lot better than 100 meters. So we beat you again. But this spacecraft and the Kunotori, they work differently. They park themselves at 10 meters from the space station, and then we capture them using the robotic arm, right there. This is the robotic arm flown from inside, and that was me actually flying the robotic arm when we capture Cygnus. And this is basically how we inside we bring all the food, our clothes, and then after we empty it out, we fill it up with everything that we have to trash, and we make the most beautiful comet. No, it's more like a shooting star. It's a shooting star made with our trash, and then we burn it in the atmosphere. We atomize it. Now this is a little slideshow of views that we have from the Earth, and here there's 2 words I'd like to say. My 2 euro cents of wisdom about these views. This is the present. This is not the future. However, I would like the future to be very similar to what we're seeing now, if not better. And the world that we live in is just like the future. It doesn't belong to you, but it is in your hands. So it's up to us to keep it going. Now a little lighter theme here. This is me playing completely alone because nobody likes my music. Karen in the earlier picture was washing her hair. This is me playing the guitar, again, completely alone. This is the look on Karen's face while I'm playing the guitar. On the space station, we are humans. We have to have our downtime, and so we do what we can. While I was playing the guitar, we play with fruit. We eat. These are scrambled eggs, and you have to know that they're scrambled eggs because we don't know that they're scrambled eggs. They have to write it here, so that we know what we're eating. How is this connected to the future? Where hopefully this is not the future, but the food of the future in space is gonna have to be something very similar. Because again, these are strawberries that have been rehydrated with a dry biscuit and some milk, rehydrated, and we call that strawberry shortcake. The food is incredibly important, and so to develop food in the future that will be more appetizing and with the right balance of flavor and taste and look is extremely important. And again, for our friends that wants to be an astronaut and go to Mars, these machines are what we use in orbit to keep our muscles working, our heart strong, and our bones in good shape. So those are the evolution of those machines. These are already very much more evolved than what we used at the beginning. The evolution of those machines is what we will use in the future when we go visit our planets. Well, this is the moment of the goodbye, so I bet you guys are all like, oh, finally, this guy's going to stop. Well, for me, it was a very sad day. This is Oleg, our commander, and this is the moment where my spacecraft detaches itself from the space station. We are inside our little spacecraft. We are inside here. And now the sky, when we look outside, is all black, completely black. When we slow down by 128 meters per second, from 8,000 meters per second, the sky becomes white. This is plasma. These are parts of the spacecraft that are burning and fly at Mach 25 next to the window. It's amazing. It's 1,500 degrees outside, about 50 degrees inside. And And it's so hot that even though we have ventilation inside the spacesuit, we are still sweating in buckets. So if there is one thing I like to say about the future is that I hope that spacecraft get better, because what we have now is small, uncomfortable, incredibly hot. But it works. Again, old systems that have been tested for years and years. When the parachute opens, we are happy as kids. We were laughing and hooting and cheering until this moment. That is the soft landing, and just like Philae, we did 3. So we landed, and then we bounced, and then we bounced again, and then we found ourselves on our side, and this is the moment where they finally take us out. When they first opened the window, the port, I was hoping to get a nice fresh breeze of air from the earth, maybe the smell of the grass. Unfortunately, all I got was the smell of gasoline being burned, because there was a little fire outside caused by our engines. But you cannot have everything. We were alive, we were happy, and we had the Olympic torch with us, which apparently was more important than the crew, because first they extracted the commander, then they extracted the Olympic torch, and then they extracted Karen, and then they came for me and they said, Luca, you're way too big. We cannot take you out, so you have to take yourself out. And it was incredibly, see all the sweat? I'm completely drenched, because pulling myself out of the spacecraft was the hardest thing I've ever done, other than the Ironman, and just about as fatiguing. And then this is the moment where we fly back, and it's not really the end, because after about 21 hours from Kazakhstan, we land in Houston. When we arrive in Houston, we just get a little peck on the cheek by our friends and family, and then we are thrown right away into more experiments. They prod us, they take biopsies from our calves, they shock us with electricity. I'm not kidding. These are all actual experiments. They take our blood, our urines, and then for days and days and days and weeks, which turn into months. And all of this is for the future, because we have to figure out what happens. I have a big head in that video. We have to figure out what happens what happens to our body before the flight, during the flight, and after the flight, and how long does it take to go back to where we were. So that science is incredibly important. It's not the end of the flight, it's just the beginning of a new phase. And the new phase also includes what we're doing here tonight. It is to talk to you, it is to tell you why it is so important to work in the environmental research, why it is so important to go look for comets, why it is so important to go from the incredibly big, from the beauty of space, of galaxies, of the unimaginable, to the infinitely small of the Large Hadron Collider. All of this is part of what we're doing now to understand where we are, but really what's more important is to see where we're going. And only you will have the answer to the question. Thank you for your attention. I'm ready for your answer.
So, again, thank you for your time. Do you have any question? For them, not for me. If you want to come over, guys, over here. Guido, Amalia, Luca. Okay, I will ask you to stand up and try to speak loud. Sorry. Go ahead.
You have seen the movie Gravity, obviously. So it is certainly a concern. I wouldn't say it's a problem. I wouldn't say it's something that astronauts are worried about. Space is really big. Even the orbits around the Earth, even though they are filling up with debris and detritus and satellites, they're still at different altitudes. So we have a lot of debris. We are trying to figure out ways to make it cleaner in the future. Actually, ESA is a project to try to clean the orbits a little bit. However, it is incredibly expensive to try to clean up the orbits right now. What we are doing now is that we are following about 10,000 of these orbital debris. 10,000 pieces. The dimensions go from a few centimeters to a lot more than a few centimeters. We are tracking them, and what happens is that whenever we see a probability of crossing orbits, we change the orbit of the space station. We do what we call a DAM, D-A-M, debris avoidance maneuver. So basically, we boost the space station up, and so by accelerating, we change orbit, we go higher, and that completely makes it impossible for the orbits to be crossing again. Sometimes what happens is that we go from one orbit into another, and then we find out that there are more debris coming into our direction. But it usually doesn't happen. So our flight controllers are incredibly good at checking their data. Now, is it a growing concern for the future? Yes, it is, because we have a lot of stuff up there. And just like Amalia said, sometimes we just have to take it down. And the easiest way to take it down is to let their orbit just degenerate until they destroy themselves in the atmosphere. But sometimes that doesn't happen. Sometimes they hit other things. Sometimes they are hit. Orbiting satellites are hit by other debris, and so this problem is probably going to exacerbate. However, the biggest problem is not really the debris. What really worries us, what would be really worrisome, would be meteorites or micrometeorites coming from other directions. Those we cannot follow, we cannot predict, and they can make some big holes. Hopefully not as big as a football field. But again, there is nothing we can do about that, and that is just the nature of the job that we do. Thanks for your question.
So I have two questions for Luca. The first one is whether the experiment, let's say, that done by Baumgartner, falling down with the special suit, is really useful from the scientific point of view, and what are the possible improvements it brought or is bringing to the technology of the spacesuit. And the other one is that, about your career, because I read from this booklet that you started in the Italian Air Force, and my question is, did you do that because it was one of the possible ways or the best possible way to become an astronaut, or because you were starting with another job and then you were selected to be an astronaut?
Wow, what a question. Okay, the answer to the first question, no. It's just about Baumgartner. It has nothing to do with spaceflight. It's a fantastic stunt. I wish I had the money or the sponsors to do it myself, just because every time I see a deep place, I feel like I want to jump myself. So, and I'm a skydiver myself, so fantastic feat. I don't think it has any real scientific value unless they're going to use the design of the spacesuit to make it more flexible. However, the spacesuit that he was using is more similar to the launch and descent kind of spacesuit that we use, not really like an EVA. And the launch and descent spacesuits, they're pretty good as we have them now. They don't need a lot of improvement. Even the future ones will not be too different. So it's a stunt. I think it's great that people do things like that, because at least people start wondering, just like you, is it a good thing? But they start thinking about other possibilities like flying in space. So I don't really see any advantage, but I always say, why not? For the second question, I still am in the Italian Air Force. And it's a mix of a lot of things. When I was a kid, I wanted to be an astronaut. And, again, it's one of my earliest memories that I wanted to be an astronaut. But was it a project or a dream? And I make the distinction. How do you become an astronaut? Do you go to astronaut school? Well, unfortunately, you go to astronaut school after you become an astronaut, so it doesn't really work. It it's one of the main problems of this job. You really don't know how and when to become an astronaut. So instead of focusing on the dream, which I think dreams are important, they give us energy, they give us motivation, they give us something to wish for, and so they're incredibly important. But rather than focusing on that, I try to think of a project, and a project is something that you want to accomplish and that you can. And it should be hard, it should have a lot of obstacles, but I really wanted to fly. And when I thought about flying, I also thought, well, the first astronauts, they were also test pilots. I could not think of a better, cooler way to follow a dream by realizing a project that is just as fulfilling. I can tell you now that if I were not an astronaut, right now I would be flying, I still am a test pilot in the Italian Air Force, and test flying airplanes was the most fun thing that I could do, other than being an astronaut. And so that when people ask me, how do you become an astronaut? I really don't have the answer to that, other than the best way to do it is to feel really happy about what you're doing, to love what you're doing, to be really good at what you're doing. And when the occasion comes up to do something better, then that's when you jump on the horse, hopefully at the right speed. Thank you.
Question for Amalia. Being an engineer, I think that we learn most from mistakes. I know that from the LHC. Do we understand what went wrong in the cartoon of Fidel?
We understand what was wrong because before starting for the landing, we received an information that said that the fuel we put inside the harpoons were not working well. The problem is that this fuel was validated for 5 years. Instead, we had a travel of 10 years. That's the problem. It was a disaster because we didn't do, after the landing, we were able to perform other experiments. So, but I think that we have to learn a lot from the mistake we did. That's the important thing. In this case, it is not clear if there is the possibility to solve this problem in future, because our travel for the mission will be longer and longer and longer in future. That means that we have to be prepared to have a solution for many years. And I am old enough to know that time is a value. Time is a value. That means that you have to think for a very long time. That's the problem.
Yeah, the warranty expired. Next time you get a warranty for more years.
The dark matter is one of the major, let's say, mystery that we are trying to face. In these days, LHC is providing collisions at an unprecedented energy, 13 TeV. Everything is proceeding extremely well after several months or years of efforts. And the secret hopes of everybody in the field is that in a day, in a week, in a year, in a decade, I cannot predict the date, we'll be able to find something really fundamental. Say that, I have to counterbalance this statement with what we see from indirect measurements. So we know that there should be some explanation of this mystery, but we don't know exactly what is the scale of energy at which we'll find the answer, the correct answer. Nature may be very kind with us, providing dark matter at a mass of a few hundred GeV or a few TeV, which is the region that we're going to explore soon. But if nature has decided to put elements explaining dark matter at an energy scale that is 20 or 50 TeV, we would need another generation of scientists and maybe another accelerator. So science is very tough, and we should be extremely patient. We are doing our best to find explanation of dark matter, but if we'll fail, this does not mean that the game is over. Another generation of scientists with new ideas and new technologies might be able to find the solutions, as we did for the Higgs boson. So this is the beauty of our field, that we might come quickly to something extraordinary, or we might wait for 25 years.
Well, if you're looking for the dark matter, you can also look in the space menu on the space station. A lot of the stuff that we eat, we think it's dark matter. It is a mystery to us.
This we'll explore soon. Thank you.
Do you need, you mean much more money?
No, money is a big issue in general in this enterprise. We are all talking of big enterprise, big international enterprise. But I used to say always, for example, take LHC altogether, the accelerator, the experiments, put everything together and have a bill. The bill is 6 billion. Euro, dollars, whatever you choose, Swiss franc, is the same money if you wish. But this is a huge amount of money, I agree, but it's 6 billion that are spent by the entire world over 20 years. This is as of today. So we have to ask ourselves, is it worth that the entire world, 6 billion people, spend €1 each in 20 years, which is 5 cents per year? Is this really something which is worth to proceed in the quest of answering the basis question, and with the secret hopes that sometime we discover new technologies that then are used for the benefit of everybody? I think the answer is, no doubt, is a yes. So it's a huge amount of money, but I think mankind is able to face this kind of investment for the benefit of mankind at all.
Guys, could we try to find a last question? Who wanna be?
There is the young girl over there.
Okay, lady.
The Mars One? So the Mars One project. You're not talking about the candy bar. So Mars One is, I don't know a lot about Mars One because it is not sponsored by any of the space agencies. It's a private enterprise, so honestly, I don't follow it personally. I know a little bit about it. I know that they did a selection of sorts where they asked people to pay some money to be a participant in this selection. And I know that the idea is to provide a one-way ticket to Mars, and then to create, in the meantime, the technology to sustain the presence on Mars. Personally, I'm not against the concept. If you think about 500 years ago, when Columbus set sail out to go to the Indies from Portugal, it wasn't much different. They were going somewhere where they're coming back, nobody knew. So as a concept, it's something that humans are able to accept. That's why we are trying to do it in a way. However, when you go into a deep a deeper technical conversation with the creators of the Mars One project, there are some basic flaws that exist even now. Now, I understand the idea of sending somebody on a one-way ticket if you can provide a very strong probability, at least, probability of survival, both on landing and once you get there for a long time, even if you want to be a Martian for the rest of your life. Some people may be happy with that. However, we don't have the technology yet. Those are all the problems that I told you about during my presentation: cosmic radiation, microgravity, closed environments with recycling water and supplies. We are not at the stage now to provide that kind of technology, and we will not be for many years. There is a reason why some of the major agencies in the world, the biggest space agencies in the world, NASA, ESA, and Roscosmos, we talk in terms of decades before committing to an idea of going to Mars. It's not because we are slow, and it's not because of bureaucracy. It's because when we do something, we want to do it once and we want to do it right. And we know that there will be a lot of obstacles on the way. So once again, it is important to look far away. It's important to look beyond the horizon. It is absolutely important. However, there are different ways of doing things, and not all ways to do things are the right way. So that's really all that I comment about the project that I don't know really well. But I'm strongly in favor of space exploration. And again, the biggest thing is to do it, to want to do it, and to look far away, think that it's possible, and influence the future starting today. So I like to have a positive approach. I like to think positively about it, with a smiling face, and do my little part, like tonight, to influence that future. Thank you.
So guys, thank you for your time and your attention. Let me thank again Paola, Federica, Guido, Amalia, and Luca. I wish you a good evening. Bye-bye.
Thank you. Thank you so much. Thank you for being here.